Hello everyone, I'm Arman Ruhi, an assistant professor at the University of Nebraska-Lincoln. Today I'm going to present you our work titled ReFACE Efficient Design Methodology for Acceleration of Design Filter Implementations. As you can see, this is a collaborative work between UNO and NJIT. I'm currently an assistant professor with the School of Computing at UNL. Before joining UNL, I was a postdoctoral research fellow at the UT Austin. I received my PhD degree in computer engineering at the University of Central Florida in 2019. As you can see, my research interests span the areas of design of cross-layer code design, for implementing data and compute-intensive tasks and applications, neuromorphic computing, secure computation, including both hardware security and security for AI, reconfigurable and adaptive computer architecture, and beyond CMOS computing, specifically using spintronic devices. So here is a table of content. So I will start with some motivations, then talk about our design methodology, show you a proof of concept, then concluded with result and conclusion part. Let me start with big data computation challenges. So as we are moving toward big data processing, current computing platforms have faced different challenges from device and architecture perspective. To name the most important ones, we have power wall and memory wall bottlenecks. Low power design is considered to be one of the greatest challenges in semiconductor industry, especially for mobile and IoT devices. And there is a lot of research going on to come up with either alternative low power CMOS design or alternative emerging technology for both logic and memory. One possible solution is to exploit the new post-CMOS technologies such as spintronics or phase change memory, etc. On the other hand, current computing platforms are based on von Neumann architecture, as you can see here, with separate memory and processing units, struggling to address computationally and memory-intensive big data tasks, and imposes energy-hungry data transfer, long memory access latency, limited memory bandwidth, and so many things. For example, based on the plot here at top, data movement between CPU and main memory consumes 200 times as much as energy as 32-bit multiplication. To overcome these challenges, one possible solution is to leverage processing in memory and process data close to where it resides. And such platform is expected to have parallelism, local data processing, short memory access latency, and low energy. Okay, so what is a residual number system, or what RNS is? Residual number system is a non-weighted number system. The unique feature of RNS can boost up the speed of special purpose computation, contrary to the conventional weighted number system, such as binary number system, which suffers from the lengthy carry propagation chain. RNS limits interdigit carry propagation. An RNS is composed of B, lowercase b, relative prime numbers, such as M1, M2, M3, to MB, where B is equal to or greater than 2, integer 2. And this M1 or any M index I is called the moduli. The dynamic range of RNS, this uppercase M, is product of M1 to MB. In such system, any integer x with x greater or equal to 0 and lower than m is uniquely represented by be tuple of non-negative integers such as x1, x2 to xb, where this xi, we call it a residue, and residue equals to the number, the x, uppercase x, mod mi. We have several arithmetic operation, addition, subtraction, and multiplication. Let's say we have x1, x and y, which are two integers with the residue representation x1, x2, xb, y1, y2, yb. Z can be computed equally by this equation, and as you can see, so you can expand it. Individually calculated the residue and then add them at the final step. Okay, one of the main advantages of RNS is that the arithmetic operation, including addition, multiplication, are performed in parallel with lower bit width over the independent channels on relatively short operands compared to their tooth complement counterparts. But unlike the arithmetic operations, there are some operations referred as intermodular operations, like reverse conversion, sign identification, magnitude comparisons, scaling, etc., which cannot be performed in parallel. It means despite the fantastic benefit of RNS, it faces some overhead for interfacing with a binary weighted number system by employing the forward and reverse converter. This figure shows a very simple conventional FIR filter in transposed form. This one shows a schematic of RNS FIR filter, and here is an RNS FIR filter in transposed form. And as you can see, almost all of the FIR filter runtime is occupied by performing MAC operation. So we have to focus on this part. We have to accelerate these arithmetic operations and expect that the whole runtime, the total runtime, reduce significantly. So to accelerate the FIR filters, we have to accelerate the MAC operation. So we came up with this design methodology or methodology to co-design efficient RNS digital FIR filters using PIM architecture. So we call it ReFACE. We utilize RNS multiplication, accumulation, and also customize PIM architecture to accelerate those operation in FIR filters. Our ReFACE takes these four inputs: a hardware description language, HDL representation of an FIR filter, configuration files, including the number of tabs, coefficients, inputs, target modular set, and device model self, including non-volatile, volatile memories, this kind of things. And finally, it produces optimized and PIM-friendly RNS enhanced FIR implementation. Okay. So it has three main procedures: generate, store, and compute module. I just give you a very brief overview of the whole algorithm, and so you can go ahead and check the paper to have a more details and better understanding. Okay, so the first procedure is generate. The generate module determines required buffer and computational subarray. It uses the number of moduli, uppercase M, and the values of moduli, lowercase n, to determine the size of both global buffer and computational subarray. In the store module, the fixed RNS filter coefficient, uppercase A, are stored in the computational subarray, Then the input signal values, uppercase X, are converted to RNS using forward conversion and store the result in a dedicated buffer. And to take full advantage of RNS, X and A input signal and also filter coefficient should be efficiently mapped into computational subarray. Then the main calculation, which is MAC operations, are performed in the compute module using modular multiplication, as you can see here, M mul and modular add or M add. The first step's final output is written back to a subarray for the MAC operation at the next level. I'll show you using a simple example. Okay. So here is our proof of concept for tap FIR filter. We consider the modular set 2 to n plus 1 minus 1, 2 to n minus 1, and 2 to n, and n equals 5, so we can get this dynamic range, which is very close to a dynamic range for a 16-bit binary values. And this figure shows a high-level view of the presented PIM-friendly data partitioning and mapping. First, the generate procedure allocate tree 1 by mn, which mn are input dimensions, buffer, and 3 256 by 256 computational subarrays consisting of data row and compute rows for storing and computing needs. Then in the store procedure, an input batch of size m by n is fed to the forward converter to provide 3 parallel channels for each integer number element corresponding to the target modular set M1, M2, and M3. Each channel is then assigned to a computational subarray address within memory, AM1, AM2, and AM3. After mapping inputs and coefficients into data rows, the compute procedure performs the MAC operations within compute rows, the blue rows, of the computational subarray. So the channel's operations are calculated in parallel. As I already mentioned, compute step includes M-mul, modular multiplication, modular addition. The modular multiplication includes partial product generation, PPG, and reduction, redo, followed by M or modular addition. In PPG stage, the first partial products of multiplication are formed by AND gates. In the redo stage, every 3 bits are summed by a carry save adder or CSA, represented by the dash line here. This process continues until only 2 vector sum and carry out remains. Both implement multiplication and addition, as you can see here, requires this red building block, which is the modular add. And finally, after completing all computations, the output is converted using this reverse converter to binary number system and go back and store in lower level of our memory hierarchy, which is DRAM here. Okay, so to the best of our knowledge, this work is the first to develop a design framework of PIM platform to accelerate RNS FIR filter. So to fairly assess the performance of the FIR filter architecture, we developed the evaluation framework and testbed from scratch. We selected the same FIR design and we implemented PIM accelerators using the ReFACE methodology based on both non-volatile and volatile memories. A 256 by 256 memory subarray for each memory technology with peripheral circuit is utilized. And for architectural level, we developed a PIM support evaluation tool on top of the MVCM to model the timing, energy, and area of various PIM technologies. A behavioral level simulator is developed in MATLAB, calculating the latency and energy that each platform spend on different tasks. So here is the plot related to the breakdown of energy consumption of RNS FIR filter for a sample 4-tap structure implemented with various PIM candidates. So top figure shows dynamic energy consumption considering PPG and redo parts in every channel. Based on our experiment results, SOTM RAM based PIM along with STTM RAM based designs could be selected as the most promising energy efficient candidates among the under test platform. And as you can see, channel 1 is the most computationally intensive layer. The main reason behind high energy consumption in the RRAM platform is costly write-back operation to store intermediate results. We observed that Sklansky adder contributes to over 80% of energy consumption in every channel. And this figure, the below one, shows the comparison among RNS PIMs with the ASIC design. It gives a breakdown of channel energy consumption for various tap sizes. As you can see, we report the energy consumed for memory access and data transfer, as well as processing it. And again, the SOTM RAM and STTM RAM designs reduce the energy consumption by an order of 85 times and 79 times compared with the ASIC design. Regarding delay, we reported the breakdown of execution time for PPG and redo as again and Sklansky adder for 4 under test PIM platforms. We observed that our RAM and SOTM RAM designs could process the RNS channels faster than other designs, and this below figure depicts the comparison among RNS PIMs with the ASIC design by breaking down channel latency for various tap sizes again. And based on this figure, RAM and SOT platform can run the 4 tap structures 12 times faster than the conventional ASIC. And finally, since floating point numbers cannot be used to implement digital filters in several cases, double precision coefficients are quantized to fixed point representations. Here to evaluate the performance of quantized RNS coefficient, a low-pass digital filter is considered, which is usually be leveraged for signal smoothing and noise reduction. We use MATLAB's filter design tool to compare RNS, a 5-bit fixed point, and a double precision design for a 10th order filter, as depicted here. The floating point implementation has a peak of 100 dB in the stop band, while using the 5-bit RNS, the stop band dropped to 87, actually minus 100 dB to minus 87 dB. And it shows an acceptable result, even with n equal 5. It's noteworthy that using fixed point coefficient in the binary domain provides lower precision than a double precision, actually, resulting in worse overall system performance. The RNS filter with n equal 10 offers similar result to the double precision. And finally, to verify the proper operation of the RNS FIR filter, we stream some data to analyze the input-output response using an RNS representation with a similar bit width, 5-bit. RNS filter presents an acceptable input-output response similar to 16-bit fixed point coefficient quantization. As a conclusion, we propose a systematic methodology to implement efficient RNS FIR filters using processing in memory architecture to address these three main issues and also accelerate the processes. Here, because of PIM-friendly architecture and RNS, the arithmetic operations, multiplication, accumulation, are performed on a small residue independently and in parallel. So significant reductions in power and latency were achieved. So using our approach, the optimum result for a 4-tap FIR filter shows this 85 times and 12 times improvement in energy consumption and execution time compared with an ASIC accelerator. Okay, so thank you so much for taking your time. I just scheme and gave you a very brief overview of our work. So please, if you have any question or if you're interested doing this kind of research, please shoot me or my collaborator Shahin an email so we can discuss more. Take care and stay safe. Bye.